Good morning, everyone. We are Hadi Hisham and Marwan Abu Dev, and today we're presenting Pixel Perfect, a content-aware super-resolution system designed specifically for retro video game assets. Our project uses an enhanced version of Earth Gone with two key modifications: nearest neighbor downsampling and a custom edge-aware sharpness loss to achieve a 4 times upscale of pixel art while preserving its unique visual style. The problem. Retro games like NES and SNES run at extremely low resolutions, around 256 by 240 pixels. When you display these on a modern 4K monitor, they need to be upscaled massively. Standard methods like bicubic interpolation just produce blurry, muddy results. And here's the interesting part. Even state-of-the-art resolution models like SRGAN and Swin IR fail on pixel art. They are trained on photos, so they interpret those sharp pixel edges as noise and smooth them out. You get this oil painting effect that completely destroys the artistic intent. What we need instead is a model that respects pixel art geometry, hard edges, limited palettes, grid aligned blocks, uh, and that's what pixel art is designed to do. For our dataset, we selected the Kaggle pixel art dataset, which contains about 89,000 pixel art images of sprites and game objects, all at 16 by 16 resolution. For our data, we split this data into an 18-10-10 for training, validation, and testing. The dataset is around 500 megabytes, which is well within collapse capacity. A critical part of our pre-processing is the nearest neighbor downsampling. We resize the sprites to 128 by 128 using neural networks interpolation to create our high resolution targets. Then downsample to 32 by 32 also using neural networks to create the low resolution inputs. This is important because it preserves the blocky geometry that defines pixel art, unlike bicubic, which introduces blur. Here you can see actual images from our pre-processing pipeline. The left column shows the raw high-resolution sprites. The middle shows them downsampled to 8 by 8 using nearest neighbor, and the right shows the processed low-resolution input that gets fed into the model. Notice how the NN downsampled version maintains hard pixel boundaries. There is no smoothing or blending between colors. This is the key insight. By training with neural networks downsampled pairs, we teach the model that the relationship between low resolution and high resolution is geometric and blocky, not smooth and continuous.
Okay, our model here is based on SGRAN, which is it stands for Enhanced Super Resolution GAN. The generator uses RRDB net architecture, residual in residual dense block network, and as you can see here, the flow is a 32 by 32 low res image enters the network, and then it passes through an initial convolution, then through 8 residual dense blocks. We reduced that number from 23 because the pixel art geometry is simpler than photorealistic images, and having 23 is overkill. And then the features are upsampled twice using nearest neighbor interpolation, giving us our 128 by 128 output. Two important design choices: no batch normalization in the generator to prevent artifacts, and residual scaling of 0.2 for stable training. Each RRDB block contains 3 residual dense blocks, each with 5 convolutional layers densely connected. The discriminator is a standard VGG style classifier with batch norm that progressively downsamples from 128 down to 4 and outputs a real fake prediction. Next. Okay, our first update we proposed is the nearest neighbor downsampling strategy we discussed. Standard SR models training on bicubic downsampled images, which are inherently blurry. By switching to NN downsampling, we teach the model that the LR to HR mapping is geometric, not smooth. Our second update is the edge-aware sharpness loss. The standard perceptual loss using VGG encourages natural-looking textures like grass or skin, but for pixel art, we want the opposite. We want hard binary edges where it fails at. We compute sober gradients on the generated image, If the gradient magnitude falls in a middle range, indicating a smooth transition like anti-aliasing, we apply a penalty. This forces the network to output either flat regions or hard regions, nothing in between. Our total loss combines L1 pixel loss weighted at 1.0 and LPIPS perceptual loss at 0.1 and our edge aware loss at 0.5. We kept the adversarial weight at 0 because it introduced noise with our limited training budget. Next. Okay, so as you can see from the training results, we trained for 50 epochs with a batch size of 64 using mixed precision training for efficiency. And we used an Adam optimizer with a learning rate of 1e minus 4. So looking at the left chart here, the generator loss in green converges very, very quickly, stabilizing after around 10 epochs. The discriminator loss in red shows interesting oscillatory behavior. These spikes represent the discriminator readapting as the generator improves, which is normal in GAN training. The right chart breaks down the generator loss components. L1 pixel loss dominates early training, and then we have LPIPS perceptual loss provides structural guidance, and notably the edge-aware sharpness loss stays near 0 throughout, meaning the model quickly learns to avoid anti-aliased edges. Okay, next. For a visual comparison, here's a side-by-side comparison. The left column shows the ground truth at 128 by 128. The middle shows the bicubic upscale, our baseline, and the right shows our pixel perfect model's output. Notice how the bicubic baseline produces harsh, blocky artifacts with exaggerated white edges and smears that does not exist in the original. Our model, on the other hand, produces an output that's visually near identical to the ground truth, which is what we aim at. It faithfully recovers the color transition and sprite shapes. Next. Okay. To validate the impact of our edge-aware loss, we ran an ablation study comparing these configurations, bicubic upscale, SGRAN without edge loss, and SGRAN with edge loss. The numbers tell a very clear story. Bicubic gets a PSNR of only 23.18 and a terrible LPIPS of 0.48. Our SGRAN without edge loss jumps to a much better score of 41.51 PSNR with 0.004 LPIPS, and with edge loss added, LPIPS improves further to 0.0029, a 27% improvement in perceptual quality. There's a slight trade-off though, 41.51 versus 41.10, but this is expected. The edge loss encourages sharper outputs which can differ by a pixel or two from the ground truth, slightly lowering the PSNR while improving perceived quality. This is exactly what LPIPS captures. Next. We want to highlight why LPIPS is the most important metric for this task. PSNR actually favors blurry images because it penalizes any pixel deviation equally. LPIPS, on the other hand, uses a learned perceptual model to measure how similar two images look to human eyes. The gap is dramatic. Our baseline bicubic has an LPIPS of 0.5082. Our pixel perfect, on the other hand, achieves a 0.0022. That's a 230 times improvement in perceptual quality, which is expected. Essentially, our model's output is perceptually indistinguishable from the ground truth. Next.
Okay, so for the SOTA comparison, for context, we compare against state-of-the-art results on Manga 109, which serves as the closest proxy benchmark. It has sharp line art and clean boundaries. The best SOTA model is WinIR, trained on DF2K, achieves 32.03 dB PSNR and 0.926 SSIM on Manga 109. Our model achieves 41.10 dB and 0.992 SSIM on our pixel art test set. Now we want to be transparent. This is not a direct comparison. Different data sets, different degradation models, and our high numbers come from the fact that we're specialized for pixel art with neural network degradation, which is inherently more structured than photorealistic SR. The key takeaway is domain-specific adaptation significantly outperforms domain general models. So for our team comparisons, I was responsible for the data side, downloading and cleaning the dataset, building the neural network downsampling pipeline, implementing data loaders, and creating the dataset visualizations you saw earlier. And Marwan handled the model and training, setting up the ESR GAN pipeline in PyTorch, implementing the edge-aware sharpness loss, configuring the training loop with mixed precision and checkpointing, and running the ablation experiments. We jointly worked on evaluation, implementing the PSNR, SSIM, and LPIPS metrics, generating the comparison grids, plotting the training curves, and results. uh, Analyzing the results. Okay, so for our conclusion and future work, to summarize our key findings, domain-specific adaptation matters. By simply changing the downsampling strategy to nearest neighbor and adding an edge-aware loss, we dramatically outperform generic upscaling. We achieved a PSNR of 41.10 dB, SSIM of 0.992, and LPIPS of 0.0029, representing a 230 times improvement over the bicubic baseline. For future work, we'd like to enable adversarial training with longer training to get even sharper textures, add a palette constraint loss to enforce limited color palettes typically for of retro games. We train on the full 89,000 images instead of our 5,000 subset. Exploring using a Swin IR transformer backbone instead of the convolution RRDB, and work toward real-time inference for integration into actual game emulators. Thank you, and our code is available on GitHub.